so let's pick up where we left off at the end of last class. Specifically, we are going to get into chapter 11, which we motivated at the end of chapter 10. So chapter 11 is on what are called random forests. This is one of our powerful machine learning algorithms, and one of the most important ones that we'll talk about in the course. And it's one that you'll probably kind of want to use at some future point, perhaps on your project here or in 490 for the final project for the project there, and so on. So what we want to do is improve on bagging. By dealing with the problem of tree correlation, which we introduced last time. Okay. So what was tree correlation? But let's just recap bagging first. Okay. So we want to improve on bagging by dealing with the problem of tree correlation. So let's just recall the bagging process, because that's going to form. It's going to be an important part of what we're doing. It's essentially what we're going to do, but we're going to make it one big improvement on it. So the idea behind bagging was to take a model such as a decision tree, or more generally some kind of high variance based learning model, and aggregate and generate lots of them randomly, and then aggregate those. So we form bootstrap resamples, so copies, so to speak, or almost copies of the training data. Okay. And then we build models on these samples. Okay, so usually decision trees, and in the context that we're going to discuss today, that's what we're going to be working in. But more generally, the bootstrapping idea, a high variance, what we call base learner. So the base learner then is just the individual model that we're going to train on our samples. But for the context of what we're doing today, random forests, this is very tree specific. So here we're going to think about these as being decision trees. And then at the end, we aggregate the individual base learner predictions. So for instance, if we're doing a regression problem, what we're going to do if we have a regression problem is we're just going to take all the individual model predictions from the base learners and output the average as our aggregation. Okay, and then we saw it's a little trickier or there's a few more options if we're doing classification. Okay, so the bagging process. So steps 1 through 3 here. Well, it improves predictive performance. And it lowers generalization error. And remember that generalization error in some sense can be thought of as a measure of overfitting, right? So it was the idea behind generalization error. It's how well does your model generalize to out of sample data. So lowers generalization error reduces overfitting. by reducing variance. Now, as we saw then at the end of our last class, and as our motivation for what we're doing today, the big problem that we run into is this problem called tree correlation. And the point of tree correlation was the same few features keep appearing in the initial splits in the individual trees. So as we mentioned, bootstrap resamples are all independent of one another process-wise, right? Like when we choose one, picking a bootstrap sample, it doesn't, what we end up with doesn't depend at all on any of the other bootstrap samples we've already picked. But the bootstrap samples are not independent as a whole because they're all dependent on the same thing, the original data, right? They're supposed to be sort of copies or facsimiles of the training data. So they're all going to look something like that. And as a result, when we grow the trees, the tree growing process is independent, and we saw that that means we can parallelize it. But the trees themselves are not independent because, of course, they're all grown on the same data, so or similar data. So then what happens is if the data is all sort of similar in the sense of it looks like the original training data, when you grow the tree, it's not too surprising then that the same features are influential at the start, right? Matter more and are more likely to be the splitting features at the beginning because you're splitting on this essentially a similar data set every time. Okay. So the solution that we introduce, it's actually quite simple, but it works very well. So take random samples of not just the data now, but of the features before splitting. So the idea is sample some, not all of the features, and only consider splits on the ones you've chosen. Okay. So this leads us then to random forests. So random forests are decision tree bagging algorithms that introduce a concept that we formalize as we call split level randomization. So the randomization now will be on both the data at the bagging level at the start, so in other words, creating the bootstrap samples, and at the level of the features when we form splits in the actual tree building process. Okay. So here's the idea. So we fix a value, and this particular value, there's different names for it. I'm going to use the same one that's used in the textbook. They call it mtry. The subscript try is basically trying to indicate this is the number of splits we're going to try. Okay. So mtry is going to be some number between 1 and p, where as usual, p denotes the number of features. Okay. So it has to be at least 1 because we have to pick a feature. There has to be a feature to split on. And the most it could be is p. In other words, consider all the features at once. Okay, so we fix this value at the start. As we'll see, this is a hyperparameter. Each time a split is to be performed, so in other words, we want to make a split in the decision tree, randomly select whatever m trie is, that number of the features and determine the optimal split. So this, of course, is what the algorithm is going to do in the background. It's going to work out all the possibilities and measure essentially reduction in sum of squares error, or in entropy or Gini index for classification problems. So however it's measuring the loss function. So determine the optimal split. But, so here's the change from what we've done before. Considering only the selected features, right? So any feature that was not randomly selected doesn't get looked at all. Okay. So what does this do in the context of the problem we're trying to solve, tree correlation? So this attacks the tree correlation problem. By hope, and I'll put it in parentheses, hopefully, because of course it's random, we don't know exactly what's happening overall, ensuring, but it almost certainly will happen, at least ensuring that in at least some of the trees, the kind of dominating features, the ones that keep occurring at the start, at the first initial splits, are selected and so aren't considered for the initial splits. Okay. And so then what happens then? Okay, so now the first, say, a few splits are quite a bit different than they would normally be. But now you've got very different structure in the nodes, right? The nodes being sort of like the partitioning of the data. And so now the later splits are likely to be different as well, because you're looking at a much different data set at that node than you would get if you split kind of in the usual way on like the kind of the powerful features, right? So they aren't considered for the initial splits, which should then result in a much different overall tree structure. Okay. All right. So that's the idea behind the random forest process. Now, what we're going to do is lay this out in a bit more systematic detail. Specifically, what does the random forest algorithm look like? Now, we're not actually, of course, going to program that, like code it in. There's packages that have already done that. But this will give you an idea when you run a random forest algorithm, what's going on, kind of as it learns, so to speak, as the algorithm runs and trains. And so I'll use this as an opportunity to introduce an abbreviation. We often write RF for random forest. So anytime you see RF, that's what we're talking about. Okay. So here's the algorithm. So step one, we start given the training data set. So essentially what we do right at the start is we initialize the training data. And this is after, say, we've split it into training and testing, right? So this is our training set, not necessarily the whole data set. We've already, if we wanted to do a train test split, that happens well before we've chosen an actual algorithm. Okay. All right. So step two, we select the number of trees to grow. Okay. And just so we can refer to it again later, we're going to call this n underscore trees. This is one of the standard R notations for it, and it gets used in packages. So, and we'll just use that for now. You can be, there's others as well. Okay. So now we're going to start growing the trees. In particular, we're going to have an algorithm for each tree that we're going to grow. Okay. So for I equals 1 to whatever n trees is, do the following. Okay. So repeat this however many number of trees times we've selected. Okay, so now I'm going to indent because this is happening, of course, for every one of these. So I equals 1, we run through the next steps, I equals 2, and so on. Okay. So step 4, generate a bootstrap sample of the training data. Okay. And then step 5, grow a decision tree on this bootstrap, on the bootstrap data. As follows. Okay. All right. So indexing again, because this is happening in the whole growing process. So for each indenting, so indexing, for each tree split, do the following. Okay, so I'm going to indent again. So this is for every one of the splits. We're going to go through the next steps. Okay. Select whatever mtry is. Sorry, it doesn't have a. I'm just going to write like this. Select mtry features at random. Number 8, determine the optimal feature on which to split among these, among the ones chosen at step 7. Okay. And as discussed before, optimal is going to mean smallest sum of squares error for regression, or greatest reduction in loss function for classification. Okay. And then once we do that, then we actually execute the split. Split the node into 2 branches and 2 subnodes based on that feature. Okay, so that's the splitting process for each tree. So step 6, let me just try to line up the 7, 8, 9 a bit better. Okay, and then so let's see. So then that ends the splitting process at that split. Okay. But then we have to decide, this is still at the level of each tree, when to stop. So use tree stopping criteria to determine when the tree growing process is complete. And so we'll see a little later, not today, but well, we mentioned it today, but we'll see next time. What do we mean by tree stopping criteria? The same things we discussed in chapter 9. So you can restrict the maximum depth, or you can implement a minimum node size that will stop splits from happening. But in particular, do not prune. Okay. So we're not going to bother, we're not trying to optimize these individual trees per se. The whole point is that the aggregation process is going to take care of that. Okay, so notice, so that is what happens for each tree. And so we're running this loop. So I didn't line up things that well, but okay. So now we end the entire process. Once we've done that for every tree. And then we output an ensemble prediction by aggregating across all, whatever n tree was, the number we did, models. Okay, so that is how random forest algorithms work. So you're going to grow these trees, and just like with bagging, it can be done in parallel because the tree growing process is independent in each case, and the bootstrap samples are independent in the sense of being chosen of each other. And same thing with the split level randomization. If you choose some features at one split, I mean, you're doing this completely at random. The next time you do a split, well, you're doing it completely at random again, right? And of course, if you're doing this in one tree, it certainly isn't affecting any of the other trees either. Okay. All right, so let's make a few comments about this process and what's going on. Okay, the first is to see that this is a big generalization of bagging. Specifically, if we set m trie to equal p, this exactly corresponds to bagging. Okay. So it's a special case with one specific value, but with a large number of features, there's a lot of flexibility here in terms of what m trie is. Okay. What are the typical values one might use? So you don't probably want to use 1, right? You don't want to just pick a single feature, because then you're not going to really have anything to compare against. And presumably, if this tree correlation problem is an issue, then we don't want it to be p. So probably want somewhere in between. Okay. So what are the typical defaults? Okay. Well, it depends on whether we're doing regression or classification. So for regression, the common default to use is m trie is equal to the floor of p over 3. And I'll explain the floor here, the notation here in a second, if you don't know it. And then for classification, we set m trie as the default to be the floor of the square root of p, where this notation, which I've been calling floor, say floor of x, is the so-called floor function. And the point of this, just to be clear, why are we introducing this notation in this function? There's no reason that p over 3 or root p are whole numbers, right? Integers. But of course, m trie, the number of features we're selecting, needs to be a whole number. Okay. So the idea, the way the floor function works, the floor of x is equal to n, where n is the largest integer with n less than or equal to x. So it's the largest integer that's not larger than x. Okay. So just a quick example of how this function works. One way to think about it, the way kind of you can think about it is it's the round down function. Okay. Or you always round down, or equivalently, you always chop the decimal part off and keep whatever's left. So the floor of 3.2, for instance, would equal 3. The floor of 2.7 would equal 2. Okay, so here's the big difference. You're not rounding to the nearest whole number. You're rounding down every time. On the other hand, if you already have a whole number, then that's its own floor. So the floor of 10 is equal to 10. Okay, but we can, so those are defaults, but we can do a lot more than that. And we'll talk more about this next week, but let's, we're going to point some of this stuff out now about hyperparameters, kind of set things up. So mtry is a hyperparameter. And so for the hyperparameter for the RF algorithm, so it can be tuned. But the nice thing, one nice observation, and this is actually true more generally as we'll see of random forest hyperparameters, but the default values tend to work reasonably well. Okay, so this is another thing. So we'll explore this more in general next time when we talk specifically about tuning hyperparameters. But as we'll see with random forest algorithms, the default hyperparameter values tend to perform well, and so random forests consequently are an example of an algorithm which is good out of the box, so to speak, or off the shelf. You don't need to tune them very much, and so that's a nice aspect of them, and they perform well even with minimal or no tuning. So make that look a little, try and make this look a little nicer. Okay. Yeah, actually, so that was the next comment I was going to make. Okay. So even more generally, random forest has good, as we say, off the shelf or out of the box performance. And what we mean by that is it tends to perform well predictably with default settings and little or no hyperparameter tuning. This isn't to say you shouldn't tune the hyperparameters. You often will get improvements by doing this. It's just if you don't, you tend to, with random forests, get pretty good performance anyway. Okay. Which is nice, because then maybe it saves you some time and so on, which is always a consideration, as we know. Okay, there are several implementations in R, but there are two common ones. So I'll mention those specifically. One is what's called random forest, as you might expect. And the other is called ranger. Random forest has more options. There's more you can play around with in it if you want. Ranger is faster. It's a faster implementation, and it's kind of designed for speed. That's the kind of biggest difference probably between the two of them. Okay. Do we, from random forest, get improvement over bagging in any examples we've already seen? Well, let's go back to our usual illustrative example, the Ames housing example.
Julian, is there any way we control number of trees in the forest as well?
Yeah, that's going to come up. That's also a hyperparameter. Yeah, we'll bring that up when we talk about. There's going to be hyperparameters for the algorithm, so trees and mtry, and there's going to be hyperparameters related to the individual trees that we're growing. So that's kind of the two things that are going to happen. So we're going to get to that here in just a little bit, actually. Okay. All right. So what we saw in chapter 9 was the best root mean square error for the root mean. Sorry, not, let me write this a bit differently. So the root mean square error that we've achieved for the best single prune decision tree that we could construct wasn't particularly good. It was about 41,000, which was worse performance than KNN and some of the other, or about the same as KNN, and worse than some others we mentioned, like Mars, that we didn't cover, but we saw produced a smaller root mean square error. So in chapter 10, what we saw was that the root mean square error for 100 bag decision trees, remembering that when we bag decision trees, we don't prune them, so we grow 100 sort of overfit, relatively deep decision trees. And the root mean square error there was quite a bit lower, about 28,000. So we got a big improvement by bagging 100 trees versus looking at a single one and trying to prune it to as nice as possible. Okay. All right. So what's the root mean square error for an RF model in Ranger with defaults? So if we use the Ranger package and we don't tune anything, we just run it on its default settings, we get an improvement to about 26,000, which is actually a pretty good improvement when you think about it. So we got a drop of 2,000, of 2,000 here in the root mean square error, which is close to a 10% reduction of root mean square error by just using this, essentially implementing this split level randomization on the features. Okay, so to get more randomness in the individual trees, and that's enough to improve. Okay. All right, so that's nice to see that this this split level randomization really can make a material difference even without any tuning. But we do want to tune if we can, and if we can get anything out of it. So what we're going to do now is lay out the hyperparameters, what they are, and we'll talk about like kind of relative levels of importance. Which ones should you focus on tuning if you're only going to tune, say, some of them. And then what we'll do on Tuesday next week is we'll actually talk more in detail about the process and about how tuning them does affect examples. And all right, so here are the random forest hyperparameters. Because random forest, it's not a particularly difficult, like complicated algorithm. It doesn't have too many hyperparameters, which is nice. We can kind of discuss them all. As we'll see in chapter 12, when we discuss the concept of gradient boosting, there's a lot more to say there for hyperparameters. And the hyperparameter tuning process has to be discussed more carefully in terms of like what steps we should do things and so on. Okay, so the first hyperparameter, as Drew kind of indicated, is number of trees. So just like what we saw with bagging, we can tune this. And in some sense, this is the most probably this is the single most important one to tune, because as we saw in bagging, it makes a big difference getting the right number of trees. So the same thing will be true for random forest. The second is mtry, so which, as we saw, was the number of features to consider for each split. The third is tree complexity, which can actually, well, it can be, there's several hyperparameters here that we're kind of combining together into one at the moment, but we can split that out. So how deep to grow the trees. We've seen with bagging already, or even just individual decision trees, there's a couple of options here. The fourth is the sampling scheme. So as we'll see, we can actually change bootstrapping a bit if we want. And the fifth is the splitting rules. So there are some additional options we can consider here in terms of how do we decide how to do splits. Okay. So during the construction of the individual trees. All right. So there's a relative importance here, and it's, I mean, essentially it's laid out that way already. Okay. So I'm going to say we have tier 1, which are number 1 and number 2. So n number of trees and mtry. These are the two hyperparameters that are going to make a big difference in model performance. Okay. So tuning these will typically improve predictive performance, reduce error, etc. So even though we saw that defaults work relatively well for random forests, you certainly will get improvements by tuning the number of trees and mtry. Sort of tier 2 would be number 3 and number 4. So in constructing the individual trees, do we want to consider the tree complexity, so how deep we're growing the trees, and do we want to think about, like, how do we sample the training data to create our samples that we're going to grow on? Okay, so these are often worth looking at, and we'll say more about this. I won't try to elaborate on that at the moment. We'll say more about that next week. Okay. And then tier 3, the splitting rule part. So number 5. So the point here is that this hyperparameter, the kind of the way the splitting rule you choose, so often has little to no effect, or even some negative effect on performance, on predictive performance. But, and this is the reason you might want to consider it, can help with computational complexity. So it can make the algorithm faster, which may be a consideration if you have a very large data set that you're running on here, lots of a very large number of data points, observations, and number of features. So if you've got if you've got really big data, then you might want to consider computational complexity. At that point becomes much more important. Okay, so this is what we'll look at next week. Let me finish up today with a review for quiz 2. So just as a reminder, nothing that we talked about today is on quiz 2, other than the fact, well, we reviewed stuff from chapter 10 that is on quiz 2, but none of the new material, nothing about random forest or split level randomization is on quiz 2. Okay, so quiz 2 is on chapter 9. So just individual decision trees. In chapter 10 on bagging. Okay, so chapter 9, so decision trees. Since this will be 9 questions on the quiz out of the 15. will be chosen specifically from concepts from this chapter. Now, of course, there's a lot of overlap between chapter 9 and 10, but specifically things related to individual trees will be 9 of the questions. Okay, so how decision trees work. I know that's kind of broad, but I just want to kind of give you an idea what kind of things to be thinking about. Okay, I'm not going to say exactly what the questions are, but just the rough idea behind what's the process of a decision tree. The idea that decision trees are non-parametric algorithms. What does that mean? Versus parametric algorithms. Always have in mind the canonical example you should have in mind of a parametric algorithm is multiple linear regression, right? Where you have a specific explicit function equation for the model. A non-parametric is where you don't have that. Okay, how do we do predictions, right? Specifically, the difference between regression predictions for a decision tree and classification at the level of the nodes, of the leaf nodes. Okay. Terminology, so all the kind of tree-related verbiage that we use. So root node. Oh, come on. Branch, internal node. And then leaves or leaf nodes or terminal nodes. Okay. Okay, so just sort of like the tree type language that we develop around this. Okay. The depth of a decision tree, what does that mean? And then how do we control it? So early stopping and pruning. Remember that in early stopping, there's two approaches there, restricting depth and bounding minimum node size. So how the CART algorithm works. So what is happening when we do the splits, and specifically how are we measuring error? So loss measurement. And so we saw there's really three here. There's sum of squares error for regression, and then there's two possibilities for classification, cross entropy, and Gini index. So know what all of these are and how they work. So when we say the CART algorithm, know what we mean by a recursive binary partition, what each of those words in the process corresponds to. How feature interpretation works. So by looking at feature importance, as we saw, and then advantages and disadvantages of decision trees as a modeling technique. Okay. All right, and so then chapter 10, of course, is on bagging, and this chapter topics specifically from this chapter will be 6 of the questions on the quiz. Okay, so remember what bootstrapping is as a process, how it works. The idea of what do we mean by base learners, in particular, low variance versus high variance and so on. And so kind of which have high variance. So those are the ones we see and improve that bagging works on well. The idea behind the wisdom of crowds we talked about. So this is sort of the philosophical kind of underpinning of the bagging process. Out of bag error validation. So how are we validating? We're using the out of bag points in the bagging process, the ones that we have left over. that didn't get chosen for the training, the bootstrap resample. How number of trees used and how it corresponds to sort of error stabilization. We want to grow more trees until we're seeing that we're not getting really any improvement in error as we create more trees. And keeping in mind, right, we can't overbag. We can't create too many trees, like that won't suddenly cause it to overfit. This problem of tree correlation. Feature importance, so the way we do feature interpretation here. Parallelization, the fact that we can train algorithms well in parallel since the tree growing process is independent, and then just general other advantages and disadvantages. Okay, I think that's probably a good overview of the different topics that we might run into on this quiz. And of course, in these are some of these go. There's more there, right? Some of them are tethers, so to speak. But I think that's a good just general layout. What kind of topics you should be thinking about questions are going to be on. Okay, so just as a reminder then, quiz 2 is tomorrow, Friday, February 4th. You can start it anytime after 8 a.m., so you can use the class time. You have 45 minutes when you start for the 15 questions. You only have one attempt, so be careful and make sure you answer all the questions. Don't leave anything blank. Don't forget to answer a multiple choice question. Sometimes in Moodle, when you click somewhere else, like you got to be careful about just sort of clicking on the page. It might like try to clear your selection. So just watch out for that. Double check at the end of when you're done before you hit submit that you've got everything filled out as you want it. And yeah, so you can do that during the designated class time at 8 a.m., but you have the whole day whenever is convenient for you to do it. If you have any questions related to quiz 2 topics or anything else, just get in touch with me. I should be available for certainly the rest of today and probably at various times tomorrow. And if not, see you next week.